Hello, welcome to part 2 of chapter 9. In this part, we will discuss representation of Boolean functions by polynomials. So, the Galois field g of 2 is defined as follows. It is a field over the elements 0 and 1, so it has just two fields. This is why it's called g of 2. The 0 is often called the additive unity, and 1 is often called the multiplicative unity. The operations over this field are addition and multiplication, where addition is simply the XOR function, and multiplication is simply the AND function. When we talk about g of 2, we denote the multiplication by product, and that is the same as an AND. And the XOR, or the addition, we denote by a plus with a circle around it. Now let's talk a little bit about the properties of g of 2. We're used to infinite fields, like the rationals or the reals or the complex numbers with regular addition and multiplication. In these fields, of course, 1 plus 1 does not equal 0. However, in g of 2, when you add 1 plus 1, it's the XOR of 1 and 1, and that is 0. So over g of 2, 1 plus 1 equals 0. So this is often referred to as the character of the field. G of 2 is a field of character 2 because when you add 1 to itself twice, you get a 0. Okay, so x plus x, or XOR x, equals 0 for every x in 0, 1. Now a minus sign in a field means the additive inverse, namely minus x stands for the element y, such that if you add x to y, you get a 0. The addition is, of course, over g of 2. This is our XOR. Okay? Now, you notice that x plus x is 0. So the element y such that x plus y is 0 is x. So every element is the inverse of itself. The additive inverse of x is at x is itself. So we can write minus x equals x, which makes perfect sense because we know that x plus x is 0. What this means is that over g of 2, we need not write minus signs. Adding x and subtracting x is the same thing. And what about the distributive law, which is one of the laws that every field must satisfy? It says that x plus y times z equals x times z plus y times z for every x, y, and z in our field. Now, how do we know that this is true? Well, we just need to check that this is a tautology, right? We have to check all 8 possibilities and see that indeed equality always holds. Okay, now let's do exponents. It's actually polynomials. X to the power of k. So x to the power of k simply denotes multiply x by itself k times, and we use the convention that x to the power of 0 always equals 1, regardless of whether x is 0 or 1. So 1 to the power of 0 is 1, and also 0 to the power of 0 is 1. Okay, that's just a definition. Okay, now multiplication is idempotent. What does that mean? It means that x to the power of k equals x for every k which is greater than or equal to 1. Okay? So what this means is that high powers of x are just equivalent to x. Okay. Now, this should be a 2. G of 2 is a field like any other field, like the reals. So the structure of the field allows us to solve systems of equations. So you can apply, for example, Gauss elimination over any field, in particular over G of 2. You can define vector spaces over G of 2, just like you did vector spaces over the reals. You can define linear dependence or linear independence of vectors over G of 2. You can define dimensions of vector spaces over G of 2 and even compute determinants and so on and so forth. So, for example, if I have this equation which says x1 plus x2 equals 0, then I know that this tells me I can subtract x2 from two sides, so I get x1 plus x2 plus minus x2 equals minus x2, right? I can subtract x2 from both sides. Now I know that minus x2 is simply x2, and I know that x2 plus x2 is 0. And I know that x1 plus 0 is x1. So I know that the left-hand side is just x1. So I get that x1 equals minus x2, but minus x2 is just x2. So I get that x1 equals x2. Okay? In fact, we can use Gauss elimination, as I said before, to solve such systems of linear equations. For example, I could add, let's give names to these equalities. I could add 1 plus 2 to get the equality x1 plus x1 is 0. And then I have x2 plus x3 plus x3. x3 plus x3 is again 0. So now I add the right-hand side. 0 plus 0 is 0. So I now know that x2 must be 0. Okay, if x2 is 0, I can replace x2 here with a 0, and I get that 3 tells me 0 plus x3 is 1, which means that x3 is 1. So now I know x2, I know x3, I can solve x1. So x2 is a 0, x3 is a 1, therefore x1 plus 1 is 0, which means that x1 has to equal 1. Okay, so we can solve systems of equations over GF2 just as we do over any other field. And now we can define also polynomials over GF2. A monomial in GF2 over the variables in the set U is just a finite product of the elements in U or a constant, 0 or 1. Okay? So an example of a monomial would be x1 times x2 times x3 times x1. You see that I have here a repetition of x1 twice, so by commutativity I can write this as x1 squared times x2 times x3. Okay? So this is a monomial. Now every monomial in GF2 over the variable u equals a constant or a simple product of variables. Simple product means every variable appears at most once, right? Why is that? Well, suppose I have such a product in which a variable appears twice. So I write here x1 squared. But now I know that x1 squared equals x1 because multiplication is idempotent. So I can reduce all the positive exponents to 1, and therefore this monomial in fact equals the monomial x1, x2, x3. So every monomial equals a simple product of variables in P, or it just might be a constant. There's always a possibility that the monomial is just 0 or 1. Okay, a polynomial in GF2 over the variables in the set U is just a finite sum of monomials. For example, I have here the monomial x1 times x2, the monomial x1 plus times x3, x2 times x3, and 1, and I take their sum, right? And we denote the set of all polynomials in GF2 over the variables in U by GF2 with square brackets U. And this just gives us multivariate polynomials as we have in the case over the reals, and you can take such multivariate polynomials and you can add them and multiply them just as you do with standard polynomials over the reals. Okay, every polynomial P over the set of variables U with respect to the field GF2 represents a Boolean function, right? You can always evaluate the value of that polynomial in the points 0 and 1. In fact, in the not point 0 and 1, over vectors 0, 1 of length U. Okay, so every polynomial represents a Boolean function. Now we claim that the converse is also true. Namely, every Boolean function can be represented by a polynomial in GF2 over U. where u is the set of variables x1 up to xn. This is a very interesting theorem because if you consider, for example, the set of real functions, then it is not true that there exists a polynomial such that, say, p of x equals sine of x. There does not exist a polynomial p of x such that p of x equals e to the power of x. So you have functions over the reals that cannot be expressed by a polynomial, right? Now, how do you prove that a polynomial cannot express these two functions? I'll leave this as a riddle. Okay, so we want to prove that over g of 2, in fact, every function can be expressed as a polynomial, which is different than what you have in the case of real functions. Okay. So I look at my Boolean function and I consider the following cases. If f is constant, then clearly it can be expressed by the polynomial, which is the constant, right? So this is easy. Now, if f is not constant, let me look at the pre-image of 1. This is a set of all strings such that f of v equals 1. Now, for each v in the pre-image of 1, we define the product, p sub v. Okay? We already noticed that we can define these products. Okay? Now, I want to emphasize that this product is not necessarily a monomial. Not a monomial. And the reason it is not a monomial is because this product may have negations of variables. It may consist of literals which are negated variables. Okay? But let's put this aside for a second. Okay. So now let's define a polynomial p as follows. It will be the sum of the products pv, where v is in the pre-image of 1. Now this looks very similar to something that we already did. We defined the DNF formula that represents f, that expresses f, to be the sum of the same products. So here we're replacing the summation, which in fact means an OR, right? This, in the context of DNF, this summation was an OR. And in the context of polynomials, this summation is XOR. Okay. So there are two issues that should worry you when you think about this proof. The first thing that should worry you is that these PVs are not monomials. Okay? We'll work that out in a second. And the second thing that should worry you is how could these two Boolean formulas be equivalent? Here I have an OR, and here I have XOR. And in general, an OR and XOR are not equivalent, right? Because the OR of 1, 1 is 1, but the XOR of 1, 1 is 0. Okay? So it's not clear that if I replace this OR by XOR, nothing changes. But in fact, I may replace this OR by the XOR. And the reason is that each one of these products is satisfied by exactly one truth assignment, and that is the truth assignment which is induced by V. So if the truth value of this Boolean formula is 1, then exactly one product is satisfied, and all the rest are not satisfied. In which case, there's no difference between the OR and the XOR. Because if I have an OR of all zeros and a 1 at the end, and I have a XOR of all zeros and a 1 at the end, in both cases I get a 1. Okay? So this explains why I can replace this OR by XOR. The reason is exactly one product is satisfied. Now let's return to the question of what do I do with the fact that this product, P of V, is not a monomial. What does this product look like? Well, this product might look like this. It might look like x1 and not x2 and not x3 say, and x4. So you see, this is not a monomial because I have here negations of variables, right? Not all the literals are positive. And in a monomial, all the literals must be positive. So the question is, can I turn this thing into a polynomial? Because I know that if this is a polynomial, then this is a sum of polynomials, and the sum of polynomials is a polynomial. And we're good again. So I don't have to have the case that these products are in fact polynomials. They need not be polynomials. So all I need to do is express this as a polynomial. And in fact, I can do that as follows. I can write it as x1 times 1 XOR x2. That would be the negation of x2 times 1 XOR x3 times x4. And now I take this expression and I open the parentheses and I get a polynomial. And this will be the sum of these polynomials, and that completes the proof. As a side effect, that for every function f, there exists a polynomial p in GF2 u such that p and f are the same functions. As a side effect of this theorem, I get the corollary that the set of Boolean connectives XOR and is a complete set of Boolean connectives. I could prove it directly, but this is a side effect of this proof. Okay. Before we complete this chapter, I want to discuss the problem of determining whether a Boolean formula is satisfiable or not. Okay, so the problem of satisfiability of Boolean formulas is defined as follows. The input is a Boolean formula phi. In fact, it is the parse tree of phi, or a string, it doesn't matter. String or parse tree, whatever you prefer, doesn't matter. And the output should be either yes or no. Okay, so we want to, the problem of determining the satisfiability of a Boolean formula is depicted as follows. We want to design some algorithm. It accepts as input a description of the formula, and it outputs yes or no. Now, when does it output yes? When does it output no? It outputs a yes if and only if the Boolean formula phi is satisfiable. Namely, there exists a truth assignment tau such that the truth value that tau assigns to phi is 1. If phi is not satisfiable, then the output of this algorithm should be no. Okay? Now, checking whether a formula is satisfiable is quite different if the description of the formula is not by a string or a parse tree. By string, I mean, something like x and y or z parentheses and w or not x. Okay? That would be a string, right? So it's quite different if I describe the formula using a string or a parse tree from the case in which I describe the formula using the truth table of the Boolean function that it represents. In this case, all I'd need to do is I'd need to check if there's an entry in the function that attains the value 1. Okay, so that would be easy. This case would be easy. But here, I'm not given the truth table, I'm given the formula. Okay? Okay. Now, the main open problem in computer science is whether P equals NP. Now, I'm not going to define these two classes P and NP and discuss what it means when two classes are equal. Instead, I will phrase an equivalent question, which is equivalent to the question whether P equals NP. So consider a Boolean formula phi. Given a truth assignment tau, it is easy to check if tau satisfies phi. Right? We show how this can be done using the algorithm eval. In fact, the running time of eval is very fast. It is linear in the size of the formula, right? In the number of nodes in the parse tree of phi. On the other hand, how can we find a satisfying truth assignment by ourselves. All we're given is phi, and we're looking for a truth assignment tau that satisfies phi if such a truth assignment exists. Okay, so clearly what we could do is we could try all possible truth assignments. But if we have n variables in phi, then the number of truth assignments is 2 to the n, okay, which is a huge number. For example, if n equals 100, 2 to the n becomes 2 to the power of 100, which we clearly cannot check all the possible 2 to the 100 truth assignments. So, what is the question which is equivalent to P versus NP? It is the following question. Does there exist a constant C in an algorithm ALG such that, given a Boolean formula phi, algorithm ALG decides correctly whether phi is satisfiable? So it will tell us, yes, phi is satisfiable, or no, phi is not satisfiable. Okay? We want the running time of the algorithm to be polynomial in the length of phi. So we denote the length of phi by absolute value of phi. This can be defined to be the length of the string that defines phi, or if you wish, the number of nodes in the parse tree of phi. Either definition is good. And we want the running time of the algorithm to depend polynomially on the length of phi. And the exponent of this polynomial, c, must be, of course, a constant. Okay? So this is the question. Can we devise an algorithm that determines satisfiability and runs in polynomial time? Now, this seemingly simple question turns out to have be a very deep problem about what can be easily computed, easily meaning in polynomial time. What can be easily computed versus what can be easily proved. Because we saw that it's very easy to prove that phi is satisfiable. All I need to do is give you a witness, give you a truth assignment that satisfies phi. And then you can very easily check that this truth assignment indeed satisfies phi. Okay? But finding a truth assignment, well, we don't know how to do that except for going over all the possible truth assignments. And indeed, this question of is phi satisfiable versus does a given truth assignment satisfy phi, this question is related to the question of whether there is a real gap between checking that a proof is correct and finding a proof for a given statement. Thank you very much.